Good afternoon, everyone. Yes, as Sarah just said, I'm Pete Bailey. I am currently chairing the Durability and Fatigue group within the Engineering Integrity Society. Right, great to see everyone. There's a few more people trickling in. I will just give you a quick introduction. So for those who aren't very familiar with us, obviously, as you may have heard the announcement, please do mute your microphone and cut your video if you've just joined. What we're going to do is we will not be having live chat, but please put questions into the chat box anytime you like during the presentation, and then we'll come back, we'll address those at the end. And that would be great. So if we just hop on to the next slide, please, Sarah. Then the Engineering Integrity Society, for those who are quite new to us, and I think a few of you are, we are a charitable organization, and our aim is really education and knowledge sharing and professional development within engineering, and particularly around aspects of durability and measurement and vibration and all the aspects to do. Our origins were very much around transport, but we now cover all areas of commercial engineering. So there are three main groups within society. There is simulation, test, and measurement. And who tend to look more at structures and real load simulation. We've got durability and fatigue, which, as I said, I chair that group at the moment. We tend to focus more on materials level characterization and behavior. And we've got sound, vibration, and product perception. And they look at things like noise, vibration, and harshness in vehicles, and that side of product perception. The fourth, as it were, group, which actually cuts across all of those, is our young engineers program, and that's that's really aimed at early career people, and trying to help them have a bit of a forum for discussion and have the chance to learn or listen to, at least, and see what they think about some of the things that people who've been in the business for longer have to say, and glean some of the things that you more quickly that you learn from working in the business, which, well, no one teaches you at university. Anyway, so that's a little bit about the society and the groups within it. Quick plug for our future events. First off, I do really want to highlight, because the closing date is coming up at the end of the month, this month that is we're running a photography competition. There are several categories within that, but we're looking for interesting images around the area of testing, and there we go. Thank you, Sarah. We've got people involved in their work. We've got looking at new technology that's being developed. We're looking at vehicle testing in particular, and then you've got the catch-all, as it were, the abstract image, which is something which is visually interesting, but can be on any topic within the field of engineering and development and measurement. The other thing I wanted to draw people's attention to is future events, as I say. So we have, this is the first webinar in a series of 4, and we've also got, our image keeps coming and going, Sarah. Sorry, I keep changing topics quickly. So this is the first one. We've got 3 more looking at hydrogen and energy storage, looking at the much more pragmatic end of battery testing within structures, within vehicles. And we've got looking at materials challenges in a wider sense for aerospace especially, looking at different technologies for this year's buzzword, decarbonising transport. I'm sorry, I'm being flippant about it. It is a very serious thing, but as I'm sure most of us have come to see, there are always fashions in choice of language. So I think we've given people a reasonable amount of time to gather and get connected. I'd like to introduce our speaker for today. This is Serena Margadonna. She joined Swansea University in 2015 as a chair in the Materials Research Centre. And since then, she's now the current head of the School of Engineering and Applied Sciences for the university. I believe her background has worked in various other universities previously, and more focusing in the past on the chemistry side of things, materials chemistry for electrodes and such like. But her work now is starting to really look much more significantly at the scale up and commercialization for industrial uses. So today, Serena, I believe you're going to talk to us just a little bit of an overview on current and future electrochemical energy storage systems, was your choice of wording, and going through various aspects, and really ending up with how near-market technologies now are going to enable more widespread and greener electrification. So that's more than enough of me talking. Serena, over to you.
Thank you. I will try to share my screen, I suppose. Sorry. Okay.
Great stuff. We can see your presentation.
Yes, this should be okay. So let me hide myself so I can go through. Okay, so first of all, thank you very much. Thank you very much, Peter, and the Society for this invite. It's a great pleasure for me to be in front of this audience. And also, as you said, I'm aware that this is the first seminar on a series dedicated to energy storage and different technologies for energy storage. So, when I sat down to decide on what to talk about, I was really puzzled because, of course, the field of energy storage is huge. There are many different technologies. Particularly, in electrochemical energy storage, many different batteries. But I thought to give a focus on those technologies that are, widespread, such as lithium-ion batteries, so that we can really look at what is now commercialized, what we have on our everyday life. And from there also making consideration on the sustainability and recycling of this technology, the current technology. And building on that, I will end with talking about future technologies. These are based on performance targets that are set for the next 10 years. And of course, the many challenges that engineers face in trying to bring this technology for the scale up and commercialization. And of course, in doing so, when we do so, we need to revise all the processes in terms of sustainability. So we look at what we call beyond lithium-ion batteries, particularly those based on the alkali metal anodes, which are the basis of lithium sulfur technology and solid-state batteries. So we'll start off, as I said, we will only talk about lithium-ion batteries for the moment. We all know that lithium-ion batteries are an integral part of our life. So lithium-ion batteries have enabled the personal electronic revolution, which took place in the early 90s. They are at the cornerstone, I would say, or they are the pillar of the decarbonization of transport, starting from the first commercialization of electric vehicles in 2010. And they are also at the cornerstone of the integration with the grid. So now there are many examples of lithium-ion batteries used in stationary energy storage, and of course coupled with renewable energy. And to meet demand and production, and of course also to increase the quality of distribution and distribution and transmission of the grid itself. Each one of these different applications, and this is only some of them. The number of applications increase constantly, and they always, there is always new one, and always require different performance, different combinations of performance. So we need to really have a diversity of purpose-built batteries, which are designed to meet a variety of applications. So that's what we need. So we cannot, while LIBs are used in all these applications, actually in reality, what happens is that we have different types of LIBs, which are designed depending on the applications that they are needed for. So lithium-ion batteries there are different types, as I said. They are based, the mechanism is the same, but what changes is the combination of active materials that are used at the positive and the negative electrodes. So in terms of positive electrodes, I think the most famous is definitely lithium cobalt oxide. I believe that this was the active material used in the first Nissan Leaf. It has a very high specific energy, however, it lacks some performance in terms of specific power and safety. There are other chemistries that have been developed, moving from lithium cobalt, and the most famous one nowadays is definitely NMC. This is lithium nickel manganese cobalt oxide. NMC is the one that is mostly used in electric vehicles. We started with the 111 type, so where 111 is the ratio between in composition between nickel, manganese, and cobalt. These have high specific energy and also meet many of the other requirements, such as specific power and cycle life. Now, of course, the problem, is a problem of sustainability. So of cobalt is highly expensive and it's very difficult to mine, and etc. Therefore, we tend to now the next generation materials for electric vehicles is all based on NMC 811, where we have the ratio between nickel, manganese, and cobalt is 8 to 1 to 1, which means that we have highly increased the amount of nickel and decrease the amount of cobalt. These have high energy, high specific energy and capacity. Also have high voltage potential compared to versus lithium, and therefore they are most used. Of course, what happens now, depending on the applications that you are aiming for, what happens that you can mix and match different cathodes and different active materials to achieve the targets that you need. In terms of anodes as well, so active materials used for the negative electrodes, the most famous, of course, is graphite, which is the one that is most used. However, there are other types of active materials that you can use for the anode. A typical one is lithium titanate. And this is because it has a high potential compared to lithium. Lithium plus is extremely safe to use because it avoids some of the most important degradation mechanisms. So if you look at this picture here we have all the different chemistries for active materials on the cathode and on the anode side are displayed in terms of potential and specific capacity. So this is where we are, and where the various, you can choose for the various application the type of cathodes and anodes that you want. This is somehow the future of where we are moving to. As you can see, most of the work is now concentrating on improving the capacity of the anodes. We are talking about now lithium silicon alloy, and most importantly also lithium metal, which is something that I will discuss even further later on. Now, how this is what about how do they work? Lithium-ion batteries. This is, of course, a picture that most of you have seen before, so I will not spend much time here. So what you have is that both the positive electrode and the negative electrodes are active materials which are coated on metal foils which act as current collectors. These serve to facilitate the transport to the active materials. As you charge the cell, so the cell is polarized, the positive electrode is oxidized, causing electrons to be released to the external circuit. So the lithium ions, they go away from the cathode, so they move away from the structure of the cathode and go towards the negative electrode, intercalate into the negative electrode. Electrons flow in the external circuit to the negative electron, reducing it, and its whole process, of course, it's geared to maintain electron neutrality. What is important to notice here is that, of course, most material, so the lithium coming out and the lithium intercalating in the charge, they all, of course, cause large structural changes within the active material at the positive and negative side. On this charge, of course, the opposite occurs, so the lithium shuffles between the negative electrode to the positive electrode. It's a shuffling mechanism, therefore it's also called the rocking chair mechanism for charging and discharging. The lithium-ion cells are complex systems. Apart from the active materials, you have a liquid electrolyte with generally non-aqueous, so generally organic solvents, and in which a lithium salt is dissolved. This increases the amount of lithium within the system. And you also have a separator, which is ionic conductive, so it's porous, so that the lithium can shuffle in and out. But of course, electrical insulating, so to avoid short circuits, so the contact between the anode and the cathode. So this is the basic principle. What I would like to stress here is that while the whole cell, of course, is a complex system, even though also only the electrodes themselves are complex systems. So they are generally composite. So we have a mixture of three main components. There is the active material, so the ones that intercalate and intercalate the lithium ions, such as, for instance, in this case, it's graphite. And this is mixed as well with a plasticizer, so generally a binder. Most use is PVDF, so fluorine-based. And then carbon super P, which is current enhancer, electric current enhancer, to maintain the electrical contact between the material, the electrode, and the current collector. So these are very, the ratio in which you mix these three components can vary. They have to be optimized. And of course, also how thick your electrode is has to be optimized. And all these parameters actually determine the performance of the battery itself. Furthermore, there is what we need to point out is that when we first charge or we first cycle the cell, we have the formation of this SCI formation. SCI stands for solid electrolyte interface. This is an essential and crucial part of your batteries, of your system. Without it, the battery will not work. It is, of course, nanometer scale, and it forms at the very first time when you cycle the cell. It formed because of reactions between the electrolytes and the surface of the anode, in this case, of the graphite. It's formed of different layers in the inner layer. So when it's the one that is attached towards the graphite, we have mainly inorganic components, while the outer layer is mainly organic components from the decomposition of the electrolyte. Of course, this is fundamental because we need to be sure. I mean, this SCI has to be to allow the lithium to diffuse through and reach the electrodes, and vice versa. This, as I said, the SCI is essential. So without it, the system will not work. And its stability, of course, is essential. If you have unstable SCI, the system will break, and the cycle life will be very low. So this is the detail that the solid electrolyte interface. This is essential, and the stability of the solid electrolyte interface determines the performance of the cell itself, but particularly the cycle life. Now, of course, the cycle life and maintaining certain level of energy density and power density are essential in a battery. So it's very important to talk about the degradation mechanisms and how these can be mitigated, particularly when we manufacture electrodes. So there are various degradation mechanisms, and they are all interlinked. I will just point out to a few of them very quickly, which also differentiate if you're looking at the negative electrode or at the positive electrode. So when we talk about the negative electrode, the major degradation mechanism is particle fracture. So the particle fracture, they break. And of course, now you have these areas in which you have to reform the SCI, and which means that you are reforming it and depleting constantly the electrolyte itself. Also, these fractures creates loss of connectivity between the particles and the connectivity between the particles and the current collector. And you can have also the lamination of the electrode from the current collector. You also have the very important lithium plating problem. So this is one of the major causes of degradation and, if you like, of fire and short circuit and battery failures, which is the lithium-ion. Instead of remaining lithium plus, it's reduced to lithium metal, and it creates its plates, so it's deposits on the surface of your particles, and creates a hotspot so that the next lithium then comes in actually deposit again, and it's reduced again as lithium metal. So this creates this formation of dendrites, of these needles like in these pictures, which of course deplete the amount of lithium that you have, and they cut through the separator, touch the cathode, the anode, the positive electrode, and of course create short circuit. So plating of the lithium it's one of the major problems within lithium-ion batteries, and how to avoid it is a major concern. On the cathode side, again, you have different type of problems, as well as particle fraction. You have the dissolution of the particles of your active material, let's say in this case a transition metal, are dissolved and go into the electrolyte, and they poison the electrolyte itself. And of course, you also have the composition and of the electrolytes that is, again, in consumption of the electrolyte, which is a major cause of degradation. So all these factors, actually, I only mention a few because they are all linked to each other. Therefore, they all have consequences, and we need to mitigate these effects at all levels. Particularly, we do this is done when we talk about the manufacturing. Okay, so when we talk about electrode manufacturing, this is differs drastically, I must say, or when we do it in a research lab, or when this is done in production plants. Okay, there are many different parameters. This is more the case on a production plant, and how the various steps influence not only the performance, but also can be used to mitigate these various degradation mechanisms. We have the slurry preparation. This is when we mix the three components of the active materials, the active material, the binder, the plasticizer, and the electronic enhancer, the conduction enhancer. They're mixed with a solvent. In the old days, they use a very nasty NMP, which is now banned in Europe, and so now all manufacturers are turning into using water. These are mixed together and to form an ink, of course. Now the mixing parameters and how these are mixed is essential, particularly because they influence the particle size, the surface area, the distribution, and the homogeneity of your coating. All these are extremely important because the particle size, of course, determines also how fracture and how much the penetration of the lithium of the ions within the particle. If you create lumps, of course, you create it's dishomogeneous, and these lumps are not electrically connected. Therefore, this we really need to optimize the parameters such as speed, mixing time for optimal performance. Furthermore, once you have your slurry, you coat. Generally, it's slot die coating. Here, the very important parameter that I should mention that really has an influence on degradation is the thickness. Because you might think, okay, the thicker it is, the better it is, because of course I can pack as much active material as possible, so I can increase the energy density. But in reality, this is not possible. You have a very optimized thickness, which is determined by the composition of your electrode. This is because, of course, if it's too thick, you will have problems of lithium diffusing throughout. You can have problems of mechanical stability. This is a huge problem because, of course, as I said, the lithium diffuses in and out of the electrode, therefore it expands and contracts constantly. This creates stress within the electrons and ultimately the lamination. So the thickness is another important parameter that has to be optimized during the coating process. After that, we dry. Drying it, we remove the solvent. Again, this is one of those steps that is essential towards to minimize degradation and to enhance performance. That's because the various parameters that you use, temperature, time, flow, airflow, so on and so forth. They all influence the microstructure, so the porosity of your electrode and the tortuosity. So the channels through it, the lithium ions can diffuse. So this is again parameters that need to be optimized. Calendaring, again, this is applying a pressure to make it more compact. This has, again, it has to be optimized for porosity. So again, this influences how much lithium can go in and out. And then, of course, it's we have the slitting, and you end up with nice coated, in this case, if it's a cathode, aluminum foil with your electrode. Now, imagine that, I mean, all these parameters, all these various steps need to be optimized for a particular chemistry, for the particular slurry, for the particular solvents, so on and so forth. Once you have the electrodes, they are assembled in a cell. In this case, we can consider, for instance, a pouch cells where the electrodes are double coated. So you stack the electrodes one on top of each other to achieve the energy that you need. This is a nice picture to show how the electrodes are stuck to one another. You can see the separator, which is in between, which is taken out of the pouch cells together with the tabs. And you can see the various layers there. Once you have packed all this, you have the tabs. You fill it with an electrolyte, and you finally can proceed to the various protocols for the formation cycle. So that's the first cycle where you form the SCI, and therefore there are various different protocols to optimize the SCI formation, which in turn determines the performance and the cycle life. So each one of these steps is the electrode, to just the electrode manufacturing. It's fundamental to be monitored in order to achieve, to diminish the possibility of degradation, to achieve maximum performance, and hopefully to make sure the safety of the system. Now, I said that I will be also talking about environmental impacts. So these are very interesting slides that I took from the ReCell Center in the US, which is a center completely dedicated to life cycle analysis of batteries and recycling. What strikes here is that if you look at the various environmental impacts, the production of the cathode powder, so of the cathode powder is the one that has the most impact towards the environment. So it's the ones, for instance, they consume most energy, together with, of course, the cell production. So the production of the NMC 111 is a very huge impact on the environment. And to my surprise, I have to say, when I read the paper, when we move towards the newer cathodes, which, as I said, now they are called the NMC 811, these are even more demanding on the environment. They have even further impact on the environment. So this is something that really needs to be addressed if we want to meet our targets. After you have the cell, very quickly, the cells can be assembled in different formats. So you can have, this is very, very famous, cylindrical cells, and then you can have prismatic cells and pouch cells. The type of format really depends on the application. And each one has pluses and minuses. If you are looking for mechanical stability and integrity, prismatic cells are most used. If you're looking for high energy density, the pouch cells are most used. Once you have your cells, you put them together into module. You form a module, and then modules will bring together to the pack, forming the pack. So these are the packs, the packs, for instance, of that we have in electric vehicles. There is a whole world of battery management system research. This is the system that monitors the pack and with various parameters to make sure that the operation of the lithium of the batteries is actually safe and within predetermined conditions. So that the battery, so it monitors, for instance, changing temperatures and changing voltage to avoid, for instance, explosions, to avoid the thermal runaways, and to avoid short circuit, including transformation for overcharging. The research here, I will not enter into this is not really my field, just to say that there's a huge amount of research going, particularly in smart battery management systems, and there is quite a work done also from the AI community, the artificial intelligence communities, to be able to monitor at the cell level to identify which of these many cells is the one that causing major problems within the pack. Again, if we look at environmental impacts, now we are considering the environmental impact for the production of a battery pack, or 1 kilo of battery pack of a standard lithium-ion battery cell, NMC111, with graphite. Again, what we notice is that if we look at the various environmental and the various criteria, the battery cell is the one that has the most impact, together with the gray, which is the battery management system. Therefore, if we look at the battery cells, if we want to look at sustainability, we really need to look at how the materials that we use for the production of the batteries, so the active materials, but also at all the manufacturing process. So this is where we are now. So this is lithium-ion batteries, their performance and how they are made. Of course, what is the future? So what is that we are requiring in terms of energy storage for different applications? So, for instance, here is a table which shows what is required for EV applications. We need to definitely increase the energy density, definitely decrease the cost, definitely increase the cycle life. We need to drastically reduce the impact on the environment, and we have to increase safety. Now, even only considering EV. Okay, so the electric cars, it's not possible for one single system to achieve all this. So we cannot use only and exclusively lithium-ion batteries to achieve all the decarbonization of transports for all different types of vehicles. We need to target and develop batteries for particular applications. This is even more evident if we look at this spider diagram. These are two main applications. A is electric vehicles and transport, and B is the grid. You can see that the demands and the performance level for these two different applications are completely different. Therefore, it's not one single battery, one single system cannot fulfill all. And therefore, we need to really now look at and have a bottom-up approach. So we need to use different materials, chemistry, and electrode architectures so that they can be mix and match to produce batteries with a variety of performances and targeted performance for each application, which span a range of energy density, power density, capacity, charge and discharge time, cost, particularly lifetime, and safety. And of course, if I might add, also sustainability criteria. For this reason, it's essential that we look at beyond lithium-ion batteries. So we need to look at new technologies which are more sustainable, the promise to meet all the targets in a more scalable and sustainable way. Of course, the most famous one is sodium-ion batteries, and this is because sodium has, I would say, it's a more democratic metal, alkali metal, in a sense it is available everywhere. Sodium-ion batteries are slowly catching up in terms of performance with the lithium-ion batteries, even though they are inherently more geared for stationary application, because of course sodium is bigger, is slower, and therefore there are concerns. I mean, there are problems of power density. Even though the functioning mechanism sodium-ion batteries are similar with the lithium-ion. But the next big thing, I would say, the near-to-market technology is definitely the lithium-sulfur batteries. These ones, the lithium-sulfur batteries promise much higher capacity and energy density. If you only consider the theoretical gravimetric and volumetric energy density compared to state-of-the-art lithium-ion batteries. However, there are many problems which have been slowly solved. It's a very complex mechanism which occurs at the cathode, at the positive electrode side, and very interesting, which are now actually being slowly solved. But the major problem, the major concern is at the negative electrode side. Here we don't have a graphite, we don't have a carbon, we don't have an intercalation type material. What we have is simply lithium foil. This, which is thickness varies depending on the energy density and the sulfur loading. Generally, we are talking about around 100 microns lithium foil. The use of lithium foil is the major concern, and it's a bottleneck because, of course, here we are changing the mechanism. So we are not shuffling lithium plus from the positive to the negative side and vice versa, but we are plating the lithium ion on the lithium foil. So what we have a reduction of lithium from lithium plus to lithium metal. And this, as I mentioned before, has some problems in terms of in terms of dendrite formation and cycle life. So while many of the problems on the cathode side have been resolved, there is still a huge bottleneck in the case of solving the problem on the lithium metal side, which is particularly in terms of scale up. So just to give you an idea, this is our own data which we have of a cathode of lithium sulfur. In collaboration that we have a collaboration with Monash University, and you can clearly see the level of the capacity that we can achieve with lithium sulfur batteries, and also the cycle life. However, the collaboration, when we transfer these results in a small scale in lithium at coin cell level, when we transfer the technology at pouch cell level, so when we have much larger area electrodes, things are not as straightforward as they look, and so we are now trying to reproduce and to make sure that the same performance that we see at coin cell level, so when we have 1 centimeter square type electrodes, can be transferred to 20 centimeters square. However, the future, and I'm conscious of time, so I will go through this briefly. The real future is in enabling the use of lithium and sodium metals as anodes. Okay, exactly in the same way as we saw for lithium sulfur. Good enough, the father of lithium-ion batteries, and actually consider implementing such anodes as really the holy grail. This is because of the high energy densities, of course, and the lowest possible redox potential, which means that I can really increase the operating voltage of the batteries, increasing energy density. And they are at the basis of all next, almost near to the market technologies, not only lithium sulfur, but also solid state batteries, which are again the next big thing in energy storage. The problem of enabling such anodes, it's all down again to what I told you at the beginning in the discussion that we had of the SEI formation. So the SEI that is formed at the phase cycle is really unstable. It's not homogeneous, and it breaks, it reforms constantly. And therefore what we have upon cycling is the formation of dendrites. So the lithium metal develops in this fashion, as you can see on this slide. This is my own formation of dendritic sodium on a copper. And this is the major cause of battery degradation, and the reason why such technology really have a short, they are not yet there in terms of cycle life. There are many different ways we can solve this because it's all a problem of the SEI. You can change the electrolyte composition. You can change the electrode design by encapsulating the lithium in different matrices, or interface engineering. That is what we are now doing for our work on lithium sulfur batteries. So what we do, we deposit a nanoscale artificial SEI layer on top of the lithium metal. This is artificial, so we decide the composition, and we make sure that it's also mechanically stable. Therefore, the lithium, it has to be, of course, ionically conductive, and the lithium can shuffle in and out of this stable layer. And of course, and you can plate and strip, so it can go from lithium plus to lithium zero and vice versa, throughout, without breaking and without modifying the solid electrolyte interface. This means that if we are successful, we will not form dendrites, and we will increase inherently the cycle life. Indeed, there are many different ways in which you can approach the formation of the artificial SEI. What we do, we deposit. So we use molecular vapor deposition techniques. And here you can clearly see some results. Again, what we have done here, we have deposited a 15 nanometers alumina layer on top of a copper. And we proceeded in the plating of lithium or sodium, in this case is sodium, and stripping of the sodium in and out of the copper foil. And you can see this is without the alumina layer. You can see clearly the dendritic formation, while this is with the alumina layer. And I think it's very clear that the morphology and the homogeneity of the sodium that has been deposited is completely different. So the effectiveness of such an approach is actually visually evident. We do this through, of course, we look at scale up. So what we do, we deposit such layers through molecular vapor deposition. These are instruments that are commercially available, and they are constantly used in the semiconducting industry. But now, in collaboration with the company that manufactures them, we are modifying them for energy storage work. And we use this type of system because we can have batch production, so we can actually reach all the targets level of production of anodes per year. And also the advantage is that we can directly coat on both sides of the lithium foil or the sodium foil, and therefore we can move on for the direct production of, for instance, pouch cells. So I think that I will finish here because I don't know why I ran out of time. But in summary, lithium-ion batteries technologies are ubiquitous, and they will continue to have a major role in our lives. However, they have limitations. The performance has reached the plateau. Therefore, we need to move on from lithium-ion batteries for particularly targeting different applications and to address sustainability issues. The holy grail in all this is the usage of alkali metal anodes, which will enable technologies such as lithium sulfur or solid-state batteries. And however, when we do this and when we develop these new technologies, we should never forget that we need to couple the scientists, the researchers that run, and they always claim incredible performance at coin cell level, with what actually happened in the industry, which is on a completely different scale. So therefore the engineers always try to run after the researchers to try to meet those performance that are obtained at small scale and are so very difficult to obtain at large scale. And with this, I will stop by thanking, thanking the many people that work with me and all our sponsors, and also to mention that in Swansea University, we do have large expertise in energy storage, and in particular looking at manufacturing and scale up. And now this is me done. I can't see anybody.
Thank you, Serena.
I can't see, so I will stop sharing.
Interesting presentation. We've got a couple of questions come through in the chat, and in fact a little bit of a debate going on there. Firstly, just let's start with a quick one, which is a useful thing, and I think I know the answer here, or at least part of it. We've got a question about what happens to efficiencies as batteries age, and do we ever get 100% of the power we put in back out?
No.
So how, just perhaps to build on that, it doesn't, but how much drop-off do you get with aging of the battery in proportional sort of terms?
Okay, so it really depends. Okay, it depends on the chemistry. It depends on the manufacturing. It depends on the various parameters. Okay, so what we generally aim for, particularly for when we look at alkali metal and deposition and et cetera, we look at 99.98% efficiency. But there is always a decay per cycle, and which at the end determines cycle life. So for electric vehicles, standard lithium-ion batteries, let's say, they are considered end of life. It's considered when you have reached the 80% of the original capacity, which means that for each cycle, your efficiency is less than 99.9%. Okay? So efficiency and cycle life are the major problems, yes? Mm-hmm. And how efficient we can pulling lithium in and out of the electrodes.
And I suppose how how rapidly the degradation and the things like dendrites and so on form in those layer the SEI layers that you were talking about. I suppose are the governing things. We've got a comment from Claudio. He's saying they've been looking at vibration effects on battery cycle life, and he's seeing that. This. I'm inferring that this is empirically from their measurements. They're getting decrease of up to 30% in the battery life cycle, just really from the introduction of the vibration. And he's asking if you've got any seen any data on what that interaction might be.
Actually, this is a very interesting topic. But I honestly don't have data, or I really don't know much about this. Being complex, what I can think of is that there being complex systems with many interplays. There is vibration we might influence, and we also might change, I would say, the electrodes structures, the electrodes composition, the SCI interface. So it's that's what but I don't have any further information.
That's fine. It's not been within your purview so far. I think putting in a quick plug for. I think it might be interesting to look at one of the next seminars within this series, where I'm sorry, I've forgotten our presenter's name, but a colleague from Horiba Mira is going to talk at sort of pack and structural level, and I suspect he'll have some data and may have been seeing some similar things. So we're very close to time. So just Alan has come back with a bit of an extension or a clarification to his question. He's saying when the cell degrades by 80% from, for example, 50 kilowatts down to 40, he's saying what's the amount of grid power needed to push the battery up to 40, to charge the battery to 40 kilowatts? So I think he's talking about charging efficiency in terms of power in versus power that you can extract.
So what you're talking about, the difference between charging and discharging?
Yes, I think that's
Yes, I mean the difference between charging and discharging is again one of it's a big issue. But how much power you need will really again depends on the chemistry, and depends on the mechanism, and depends on the anode.
Does it also depend on the charging rate?
Absolutely. Okay. Things change. The mechanism. That's also the trade-off between power density and then specific power and energy density. So power, it's always a trade-off. So how much you charge and discharge, and how much you can put in. So it's always a trade-off between those two.
Okay. Well, I think we haven't. I think I've covered the questions. Oh, Robert has commented, I'll never again refer to a simple battery, not even lithium. It's a fair point, and I think an important thing we should take away. We have hit 1 minute past 2 in the UK time, so I'm going to wrap up here. Serena, thank you very much indeed for your time and for a great presentation. If people do have further questions or comments, then please feel free to email into the society to the info.eis, and we'll try and sort that out. I think we'll probably be able to make the slides from the presentation available on our website. I'm not sure if we confirmed that in advance, Serena.
Oh, yes, 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 yes.
That would be brilliant. So yes, they'll be available through the EIS website for members. So once again, thank you very much, Serena, and we're going to wrap up, and I would wish everyone a good afternoon.
Thank you very much. Bye.